Good evening, Year 13s. So this is the second lesson in our flipped classroom biomechanics sessions, and I hope you have watched the one on force summation and found it quite useful. Now the one that we're going to be looking at today is about projectile motion. Okay, so projectile motion is all about the motion of a projectile. Okay, so firstly let's have a look what a projectile is. Now a projectile is anything moving in the air, and that could be, in this instance we have the motorbike, okay, and also the person. As soon as it enters into the air, where we have things like air resistance and gravity going against it, this is what we consider a projectile. Now it could also be a ball as well. So just as we have here, we have the little cartoon throwing the ball into the air. As soon as it hits the air, it becomes a projectile. As soon as it hits the ground, it is no longer classed as a projectile. So what we're looking at today is the projectile motion. Now if we have the flat ground here, okay, and I have a cricket ball in my hand and I throw the cricket ball in this direction, the path that it will take looks like this. Now this is called parabola. It's a type of curve where if we were to draw a line down the middle, it would be equal on both sides. That's if there is no wind in either direction. It would take a perfect parabola. Now the reason why the ball does not continue on this path up out of the Earth's atmosphere is the force of gravity. Okay, so when we have the cricket ball in the air, there are two forces acting upon it to stop it. Now we know that with Newton's first law, the law of inertia, it will remain, the cricket ball will remain in motion, in this motion, unless an external force is applied. Now the external force that we have here coming straight down is gravity. And acting against it that way is air resistance. Now these two forces combined create this parabolic effect. So as the ball goes around to here, we still have air resistance against it and also gravity. Now gravity is a constant at 9.8 meters per squared, and air resistance is dependent on the size of the object, the wind, and surface. So the size of the object, the larger it is, the larger amount of drag that it can create. The prevailing wind, even if it's a headwind or a tailwind, or the surface of the ball. So the surface, a good example for that is a golf ball. Okay, so let's go back. So we've got our flat ground. We have our cricket ball and the different phases of that parabolic path. Now remember, we always have gravity acting downwards to a certain point where the acceleration of the ball upwards matches gravity, and that's at the top of the parabola. We still continue to have the force down, and then we still have the air resistance going that way there. So gravity, air resistance. So it affects the projectile the whole way through, all the way till the ball hits the ground. Now let's have a look at this concept called drag that I alluded to before. Now I said the larger the object, the more drag it creates. If we have a ball the same size as a beach ball, and then a cricket ball here, we can add how the air acts around it. So the air is represented in parallel lines, and as the air flows around the ball, it doesn't go through it, it goes around it, and then what it does is it goes back into those parallel lines. And what we have here created at the back is what's called a negative air pressure. Which actually brings the ball back, or stops its acceleration through. If we were to have a look at the smaller ball and we draw the air going around this ball, we can see that this zone, this negative air pressure, is a lot smaller. So that's why we can kind of hit a golf ball much further into the, much longer, rather than at something like the same size as a basketball. Okay, so this is how air pressure and air resistance works. So let's write this down, air resistance. Now, let's have a look at this concept called gravity. Now, one day, there was a guy called Newton. He was sitting under a tree, sitting under an apple tree, minding his own business, when an apple fell off and hit him on the head. And this is where we had the idea of gravity. So we have gravity. And gravity is a force that's pulled towards the center of the earth. So you have the center of the earth there, and we have all the way around. And as the earth spins, it creates this consistent force all the way in towards the center. Okay? And that force is 9.8 meters squared. The pace that something will move down towards the center of the earth. So we always have those two forces acting upon a projectile. Now let's have a look at the three conditions of projectile motion. The first, how we can manipulate it, is the speed of release. The second is the height. And then the third is angle of release. So first, let's have a look at speed of release. If we have the object here, which we're going to throw, if we throw it at a distance of, say, 20 kilometers per hour, okay, that means that the air resistance takes off roughly, let's say, 2 meters per second. So for every meter it goes, it takes off 2 meters per second. Okay, let's change that to meters per second as well to make it a little bit easier for ourselves. So when it gets to Mach 1, it will be 18, meter 2, 16, 14, 12, 10, 8, 6, 4, 2, 0. So we know that at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 meters, the ball will have decelerated to 0, which means it would have hit the ground. And with gravity acting upon it, it will follow this parabola path all the way to there. If we were to release the ball at, say, 10 meters per second, again, air resistance takes off about 2, so we go 2 meters per second. So here we go 8, 6, 4, 2, 0. So if we release it at half the speed, it will in theory go half the distance. So when we look at speed of release, the quicker that we can release the projectile, the further it will go. Now let's have a look at our second one, and that was height. We have a ball on the ground, and we know that if we throw it at a constant speed at the optimum angle, it will follow this parabola path. Okay. We know that how gravity and air resistance affects the projectile, and we can be pretty sure that this path will be a parabola. If we release the ball all the way up here, it will too, and this is on a cliff, it will too, in theory, follow that same path to there. But seeing as though it's not going to hit the ground, the ball, it will continue on this parabolic path down to meet the ground there. So this first time when we threw it at the ground level, it followed this parabola path and hit the ground there. If we increase the height, we still follow that parabolic path, but instead of stopping where the ball was released, it keeps on going until it reaches the ground. And we can see that the higher that we release the ball, the further the ball will go from point X, which is our origin. Okay, so this was height of release. And we can say that the higher that we release the object from, the further it goes. Higher equals further. Now let's have a look at our final one, and that is angle of release. Now we need to draw some form of graph here to represent this. And if we take this as point 0, the origin, and we know that an object will follow that parabolic path, so if we throw it up and it gets to its optimum angle or the optimum height, it will follow that same path back. Okay, it will not sort of get to that point and just go straight down, only if there's air resistance involved, and we'll talk about that a little bit with badminton. So if we release it on a really high angle, when it gets to its top point, it will follow that same curve back down, so that this half is equal with this half here. Same here. So the angle of release is the angle between the ground and the original trajectory of the ball. Okay, so if we expand that a little bit more, so we have the ball going in this direction to start off with. The angle of release is there, that angle there. Now the higher that we release the ball, and it gets to that point where it starts to come back down again, the higher we release it, the least distance it will go. But also, the lower we release it, gets to there, follows that path down, the less distance it will go. We need to find an angle in the middle, that when it gets to the top of its curve, it will come down following that same path, so that this side there and that side there are equal. And the optimum angle is 45 degrees. So we've shown here how too much of a high angle affects the projectile's motion, too shallow an angle affects it that way, and the optimum angle will give us the greatest amount of distance. So in class tomorrow, what we will do is expand projectile motion a little bit further, giving some more activities towards badminton. Hope you enjoy, and see you tomorrow.